Buonasera a tutti, sono Giorgio, presidente di EPS Young Minds, sezione di Catania, e ho il piacere di presentarvi oggi un'intervista al professor Martin Pumera. Devo fare un piccolo disclaimer all'inizio. Questa intervista sarà in inglese, quindi attivate i sottotitoli se non... Ora, chi è il professor Martin Pumera? Martin Pumera è il capo del laboratorio Future Energy and Innovation Lab a CEITEC a Brno in Repubblica Ceca. È anche il capo del laboratorio di Advancement in Nanorobotics e Multiscale Robotics all'Università di Ostrava in Repubblica Ceca. E se dovessimo elencare tutti i titoli che gli sono stati affibbiati negli anni, non finiremo più. Però alcuni devono essere menzionati perché sennò non si capisce di cosa stiamo parlando. I suoi interessi spaziano prevalentemente nei nanomateriali e nei microsistemi. Oggi parleremo un pochettino anche di nanorobotica, capiremo un pochettino meglio. Ha pubblicato più di 1 migliaio di articoli e ha ricevuto molte più citazioni, quindi sulle 60.000-70.000 citazioni, e questo pone il suo H-index al momento a 127, che è un numero, per chi non ha le conoscenze di base, un numero piuttosto alto. Detto questo, ora passerò in inglese, quindi thank you for being here.
Thank you for the invitation.
First, I want to ask you about what are you doing at the moment? What is your research topic?
Yeah, so we do everything we like to do, which is a very broad definition. So I basically put it in the way that I'm a materials electrochemist, but our interest is quite broader because I feel that doing for 20 or 30 years, in my example, actually I do chemistry since I was 14 because I went to chemistry high school. So for 36 years to do the same is kind of boring, so we try to invent. And I always say it's really important to bring something to the current state of the art and current state of the science. So we develop the topics developed. So I used to work with carbon nanotubes. I don't work with carbon nanotubes, not that they are bad materials, but I don't feel I can bring more to it. Maybe some people can, but we cannot. I don't work anymore with graphene because we brought what we could. I don't think that we can bring more. So we basically use what we learned before and we apply it to different materials which we feel is either they are at the cutting edge of the science or we develop new direction in the science. I would say not main direction but sub-direction, and this is what I like to do because it's very difficult for anybody to chase the development of other groups because they are already 2 years ahead. Because if they publish something, you try to chase something, they are already published, working on different publication. So I like to choose the topic I feel is perspective, but nobody works on that direction, and I try to put several people in my group on that direction, and we try to go forward, and most of the times we get quite far and people chase us. Sometimes we just hit the wall and it's not perspective, but that's life. So, but I didn't answer your question. So we work on is basically materials wise, because this is physics department, we still work on 2D materials, but different than graphene. We work also on 3D printing, which is somehow, when I mention that, people ask, what can you invent in 3D printing? Because you can buy 3D printer to your home, right? You can 3D print home. So how can you do research on the 3D printing? Actually, you can, because there's lots of electrochemists or lots of material scientists want to use 3D printing, but when they buy the machine, they run into lots of problems for their applications, and we solve the problems because we have the same problems. So basically, we solve problems for them, and they can kind of follow us. So this is 3D printing. We do lots of nanorobotics because this is interesting application of nanotechnology or microtechnology. And we currently work on single atom catalysis, single atom engineering. So this is from the technology point of view. And for the application, I always like to see that our work has some outreach. So we don't do just basic research. Even I enjoy very much basic research, but we also see that this can be applied potentially. So we work on the 3 different domains in biomedicine, in environmental remediation, cleaning of environment, and energy. So we have 3 application areas and 4 kind of technologies we apply to those.
So what future development could micro and nano robotics have, both in terms of methods and fields of applications?
There's always question if you are asked what are you going to do in 2 years. I always reply if I knew what I'm going to do in 2 years, I would do it today, so I'm 2 years ahead, right? So what future developments, I don't know, honestly. So what we are going to do in 2 years, it's a mystery. Obviously, we have directions, so I can tell you what directions I see as a perspective, but things can change quite quickly. So basically, there is still lots of space for understanding on communication between the robotics, or between the robots, because they are basically inorganic particles, can be also polymer particles, but basically they are dead matter, that's not live matter, but we try to induce communication between those robots. So basically make the swarming behavior, make the memory in the robots, which we also work on this in our group. So basically robots can remember, for example, acidity of the environment they went through by changing the structure and therefore light they emit. So they kind of can remember some things. So how to kind of upscale this and make them to behave more as I would say artificial organisms in the sense of function, not in the sense of multiplication. But so this is one direction on the fundamentals, but of course those things can be applied. So there's lots of huge move to the applications, especially biomedical applications. So lots of groups look at biomedical application of the robots. For example, those color-changing memory-based robots we use, for example, for determining whether those robots went through acidic media, whether what they found in the stomach, what pH, and so on. So you can look and you can use your imagination. But as I said, basically what is hot in 2 years, nobody knows, but basically the momentum is towards biomedical applications. There is lots of groups, so I don't think that this momentum can change, because the train is already on the way. So in 2 years, it's clear what is going to be in 5 years. It's much more difficult to predict, and I see the communication between robots is still a big question and issue. So that's also something which we should, as a field, work on.
Some curiosity about the programmation of those nanorobots. I mean, in common use, we have robots, something like the Roomba, which are programmed by developer. And how do you actually program? I know that they are not real robots, but how do you program them?
Actually, the question is, what is the real robot? So, do you know where the word robot comes from?
Automation of something?
Yeah, but the word robot, like you have word pizza, maybe it comes from something. So, word robot comes from some language. Do you know from which language it comes? It comes from Czech language. So I'm Czech. Hello. So it comes from the Czech language, and the robot is from word robota. And it's forced labor. Robota is forced labor from Mediterranean, not Mediterranean, Middle Ages, not Mediterranean, Mediterranean is here. So from Middle Ages. And we had a play written by famous writer at that time, about 100 years ago. And the play was called Rozum Universal Robot. And the word robot was not known that time and was invented by the writer based on the robota. And Rozum mean mind, but Rozum means also name of somebody, so it's kind of playing with the words. Anyway, so what is the robot about in that play, which is the first ever written description of robot, ever, because he invented the word. So the theatrical play is about android, so basically it's human-like, programmed person. It's not like some mechanical beast. It's really kind of human-like android, which what this robot lacks is the empathy and feelings. And towards the end, the humankind dies, and the two robots, which are androids, so it's like two of us, it's male and female, but they're androids, so there's nothing special about it, and they start to feel love, and the game ends, so it means like humankind will be carried out in the feelings of those robots. So the robot as a Roomba or the automatic electronic thing is kind of new invention. So our robots go back to the speed, they don't have feelings, but they can be programmed as those androids. And so our robots are mechanical things like those 100 years ago. And you can basically make material which, like gummy bear. You know gummy bear from Germany. You put gummy bear, it's a robot, yeah? I mean, it doesn't move, but if you take gummy bear and put it in a flask with the water, it kind of soaks the water and expands, right? So you can say, I programmed this to expand. Okay? So I can play with the same. So I have a robot which I can chemically change that if it, or put surface that if I put it in some environment, it does something. So it's programming, right? So it's like basic language. I did basic programming when I was 10, 12. If this does something, goes to line 20, if it, whatever, changes the light to red or yellow and moves 2 steps ahead, and then if this happens, so this is programming. So you can program the robot, you can make the layers on the robot, and if it reaches acidic solution, it dissolves, and if it reaches something, change colors, and so on.
So it's more of a physical and chemical.
Exactly, and it's kind of like almost like basic, the basic programming language, not C++, because it runs, and at the end, it ends, right? So our aim is maybe to have the robots which are recyclable, which can kind of run in the cycles. You don't want this kind of run and it's over. So it's really chemical and physical programming, which is not less important than normal programming, because actually as biological entities we are programmed in this way, right? So we are not programmed by electronic signals. So, so this is how it is done.
Thank you for the answer. Then now for the next question. It is now confirmed that plastic are present in our blood. Research from a teacher from university has been published, which states that. But what tools or alternatives could research and innovation suggest to reduce microplastic pollution?
Well, I don't know. I'm not from microplastic field, so this is the question I honestly would say I don't know. But what we actually do with the robots, and we try to have, because the micro nanoplastic is of the size of micro nanorobots. Okay, so our way to look at this is you can use filtration to remove, but you know, to remove microplastics, for example, but then you remove lots of other things as well. But we can use robots which actually can selectively trap microplastic and remove. Okay, or we have a robot, we can program robots which can actually trap the microplastic and digest, partly digest. We cannot remove, kind of digest it completely. So those are the ways. I mean, we work on this in this field for a few years. So, and there's only a few groups, mostly our group and a couple of groups try to follow, which works on that direction. And always, I mean, every solution to the problem depends on the resources you put to the problem. So if you want to fly to the moon, you cannot have one group to try to construct a rocket, because, I mean, with the money invested, you are unable to do it. So I would say there are different ways how to look at the micro nanoplastic. Of course, obvious way not to even have the micro nanoplastic released to the environment, but since it's already environment, we have projects in our group to have robots removal of reproductive organs of microplastics, because you have them in all reproductive male-female reproductive organs. So one of the postdoc kind of came with this idea. So I said, fine, let's do it, because it's a major problem in general. You have a credit card volume of micro nanoplastic, and it's not about credit card to have it somewhere in your body, but if you look at how much powder you can generate, and it's kind of all over your body, including your brain, doesn't, at least my brain doesn't like it, yeah? so I don't know what about other organs, but certainly my brain doesn't like this idea. But we have very small, limited way to look at those things, but again, the question is, we have some toolbox, right? We have a tool, we have robots. Where can we remove the plastic? So I think the idea of reproductive organs from that postdoc is very good, because this is the way the robots can move. Can they move in liver? maybe not so easily, maybe they can damage to deliver much more than can help, right? So we are also looking at different organs, but you can start with the things which are the easiest. So this is one of the ways.
So now for the next question. What are the biggest challenges in moving from lab-based prototypes to practical large-scale application? And what steps do you think are necessary to overcome them?
Well, I think the biggest obstacle, and let's talk about environmental remediation, not biomedical steps, because there is lots of approvals, but let's talk about just simple thing, which is environmental remediation, cleaning the waters. It's simple cost. So if you look at, we talk to the water works companies, and they say, okay, we clean the water with this and this technology, this is how many cents per cubic meter. Well, I cannot ever reach this level with my technology currently, but we have talks with the companies on basically using robots, for example, for cleaning membranes. So you have biofilm, we do lots of biofilm removal for biomedical application. Biofilm is something which grows also on pipelines, grows on the water purification system. It's a major problem because it blocks the pores. So we can remove the biofilm with robots. We can also clean the pores with the robots. So this is one of the applications robots can help. And again, as I have this history of carbon nanotubes, graphene, and so on. So I worked on microfluidics before. So it was always like microfluidic will revolutionize and they change everything. Carbon nanotubes will change everything. Well, it's not the case, right? So yeah, if you find 1 to 5% of the market application for those technologies, you are lucky, and it's okay. So let's be honest. Our nanorobots will not change everything, but they will find niche application where nothing else can kind of match them or replace them. So, and of course, if we knew exactly where are the niche areas, we would just work in them with some imagination where they are. But I don't really know. So we try to look at different things like microplastic removal, biofilm cleaning, and we hope that in some of those areas we kind of feel can be really practical, so we can carry this closer and closer basically to technology readiness level. So it's not lab based, only technology readiness level 4, but we can go to technology readiness 5, so it's demonstration, and then we can go basically to semi production lines. And so we have this actually very nice collaboration with water purification company, but it's always way to find the expectations so they match. It takes some time.
So even not great game-changing results can be.
I mean, the question is like, what is the game-changing result? I mean, I'm old enough to remember the LED, right? LED, there was Nobel Prize some years ago, a few years ago in physics, I believe, for LEDs. And now, I remember 2005, I was in Japan, I was still a young postdoc, and I talked to people from Toshiba, and there was some engineer from Toshiba, poor English, but the guy was actually doing the LEDs, in the Toshiba. And I said, yeah, so what about this technology? He said, yeah, it will be on the cars, on the red lights, like backlights, but I cannot, and he told me as a Toshiba engineer, I cannot ever imagine it to be in the headlights. I said, no, this will be so weak. Well, you go to study your Volkswagen has a LED, LEDs in the front lights. So the things, game changer, at now, even they couldn't predict, and it was the technology in the industry, whatever, 20 years ago. So now what I can tell you, the robots will never do this. Well, for sure in 5 years they will do it, but I'm limited. I have one brain. In the group I have another 40 brains, but we are still limited, and this is good because there are another 100 groups. And I always say, well, this can be a problem, but then other groups has completely different approach. So they kind of don't go this way, but they go around and they solve the problem. So, we had a kind of idea about 12 years ago, published papers that it's very difficult or impossible for robots to move in the blood. And there were other groups to find, this way is impossible, what you tried, and basically what is the mainstream in the field, but that way is possible. And it's always kind of this game that you challenge other people, and they say, well, I take it as a challenge, and I will prove you wrong. And so I enjoy that, and I'm doing it with other groups. They say, well, it's impossible. Well, nothing is impossible. Let's try to go around and find a solution. So as answer to your question, I don't know what's going to be applied, but certainly I feel the technology is very exciting, and as I said, more money and more effort you put, more results you get from it. Yeah.
Very interesting. And now, how about recent physics Nobel Prize was about machine learning, and what do you see how do you see the integration of AI influencing the development and autonomy of nanorobots, in particularly in complex tasks such as environmental cleanup and medical diagnosis?
Absolutely. So if you are interested in AI and robots, please join our group. Okay. And so indeed, we work on. I mean, the idea is idea AI and robots is always about. I always say there is 20 people. If I have this idea, there's 20 people who has the same idea. You know, we are not unique. I mean, we sometimes think we are unique, but based on my experience, 10 to 20 people have this idea. And out of those 10 to 20, they have 3 of them has the resources to do it. And the question is, are we one of them? Yes or no? And are we fast enough? Yes or no? So in this case, we were not fast enough. So there is one nice paper in Nature Machine Intelligence from Kurana Group, and which I would say it's a relatively simple paper, which is not criticism, it's a demonstration. It's feedback machine learning AI motion of robots in magnetic field. We could have done it, but we are losers, we haven't. So shame on us. Yeah. So that's the always kind of makes me the most not irritated, but unhappy that if we didn't have resources or if we didn't have the idea, it's fair game, right? So they're better, faster. But if we had everything and we couldn't make it faster, then it's fair game, yeah. But it's all right. We work on that. We have this is actually one of the ways I'm happy to have the second affiliation in the Faculty of Electronics, because we have different approach. So we have people who are actually helping us with electronics, people which actually understand real AI. I'm a chemist, I don't understand AI at all, but not that I can have the dreams and ideas of how to integrate, but I cannot do the detailed work. And we have people doing this, and maybe we kind of try to develop it much more complex at the first than it was necessary, and we are second or third. It's okay. We can still make the contribution. So I always look at the research like, can we make contribution in this field or subfield? And I feel that we can still make because there is not much contribution in AI and robotics and micro nanorobotics, and I feel there is lots of space where this can help. Especially with this coordination, swarming, because you want to have the robots to come together, do something, expand, and
controlling
systems. Exactly. So this is where part of our group is heading, and of course we have competition, which is good because it keeps us healthy and vigilant. Yeah. Basically. So please join us. Yeah.
And so for the last question, what advice would you give to students hoping to enter the field of nanotechnologies?
Don't, yeah. So no, look, this is a joke, but look, I would say it's just kind of weird question. Sorry. So maybe I try to reformulate what advice. I think generally the advice to the students: you need to look at several things when you want to, and now we talk about PhD students, I assume, or master students. What students?
From bachelor to.
Oh, yeah, that's just like I would say, if you are a bachelor student, there's not much. I mean, you can really follow what you like as a bachelor student because there's not much experimental work. So basically, all the lectures, as long as you find that the university has a good quality education in your direction, it's you enter. Whether it's Cambridge or it's Prague University, something doesn't matter, or Singapore, Japan. However, when you go to masters and especially to PhD, you need to consider different things, and that's when you're a student, this doesn't cross your mind. So PhD is not PhD study; it's kind of lie. Okay, it's lie. And we lie to you. Okay, I'm sorry, I don't lie to you. I'm very honest. So I'm telling you, as a professor's PhD study is work, is a job, and now you get trained. So it's like you are at the job and you get trained on the job, but the question is what you are trained at. It's not only lectures. The lectures are a minority of the things, but you actually learn how to do stuff manually in the lab. So basically you are trained how to make something, do something, but also how to write a report. We call it publication, but it can be also in company called patent. It doesn't matter. So basically you are trained to do research. And the research has beginning, middle part, and end. Whether it's patent at the end, company, or research work, which is paper. And now you need to be very careful because you need to join the lab which has good ideas, which maybe you don't consider, you don't know because you're a student, maybe you don't know whether the good ideas are good or not. So you need to look at the students. Does the professor have some reasonable number of students? Because where do you get help? The professor is always somewhere, teaching, traveling, trying to get the money, presenting to some talks, so you need to get some help. So help is coming from your peers. So is there enough well-educated peers, or is it friendly group? And what do you learn? I mean, I learn something I like, but I mean, I don't know what I should like. Should I like nanorobots? Should I like microelectronics? Should I like flexible electronics? Should I like, I don't know, photonics? I don't know, right? And maybe you like everything the same, or maybe you prefer something, and you should actually look what professor can teach you, or the lab can teach you, where you can be at the end. So because then it determines what job you can do after. So if you are in the group which is doing high-end science, you can do, it's like high-end sport, you can do another high-end sport after. But if you are not doing high-end science in the sense of also training, so you get trained how to write high-end publications, then you may not end up in the top team at the end. So the 4 years is basically kind of a protected environment to prepare you for the real life, which comes after PhD. And now you need to choose the group wisely. So maybe too big group is maybe sometimes too big. I have 40 people. You can ask, do I talk to my students individually? Yes, I do. Many groups, they don't, because they have pyramidal structure. I have nothing against, but you need to say, well, I don't need to talk to big professors. Maybe I don't want to. Sometimes I want to. I mean, but some people want to talk to the big professor. I want to talk to my people. Then you need to say, does the group publish good journals, in good journals, reputable journals? Where are the people from that group now? Are they in good jobs, or are they looking for the jobs? Unemployed. This is also, I mean, very clear indication. So you look around, shop around, and you should follow your passion, but sometimes you also need to follow the passion in the sense of, at the university, very few universities can do everything. Top people in everything. I'm sure there are some universities. I never work at one of them, because I mean, some university is good has good groups in that direction, but maybe not so good groups in other direction, or even missing groups in that direction, in another direction. So, and if you are geographically limited, you don't go to Cambridge or Oxford or MIT, or maybe it's they have also limitations in some things. Then you need to say, well, this is top group. It's similar to what I want to do. I join that. But if you say, well, I want to just do this particular, you can do, but then you are very much geographically limited, because maybe 2 groups in the world are doing it. So you need to travel to California if they take you. So it's always kind of game, of is how limited is your idea.
As you
and
said
who
before, matching
expectations, yeah. But also, I mean, the thing is that things can be always developed, and I never knew that I will be working nanorobots. I would say, well, why? I'm a chemist, I'm an electrochemist, I would never work on that. This is very weird, robotics. I'm not a robotic guy. But over the years you change, you look for the opportunities, and you start looking at the things maybe differently. So I think very important is to approach it with open mind. And I think you need to join the group where you feel you can be somehow intellectually challenged. There is enough productivity. You need to ask what is for the field, what actually is valued after 4 years, what they look for, what you have in the hands in your CV. And you need to be in the groups where you feel good. Doesn't mean that you feel good that you go all the parties every night, but you feel good in the way that you are supported, and then people help you around. Yeah, that's my advice. So it's not about nanotechnology. I think it's for any kind of natural science field. Maybe other fields are different, but for natural science, I would say, follow what you like, but sometimes you don't know what you like, so you open your view.
Your horizons. Thank you very much for your time and your words.
Thank you.
Thank you from home.
Bye bye.
For joining us.